Thank you. Thank you for inviting me. So I'm going to tell you a little bit about our work, our research. On the screen, you can see a picture of one of our telescopes. It is nestled in a bowl-shaped ground screen, and it's sitting on top of a building, which is at the South Pole in Antarctica. So in the background, you can see the sun setting. You can see the horizon and the sun setting. So the South Pole is the Earth's rotational axis. So, of course, the sky just goes around and around at the pole. All of the stars are circumpolar. The sun, however, spirals up to 23 degrees above the horizon, and then it spirals down. It hits the horizon, it goes below the horizon, and it stays there for 6 months. So anybody who is foolish enough to witness this event is going to get stuck there. It's going to get dark. It's going to stay dark for about nearly 6 months. And they will then be trapped there because the planes that surface the site only operate during the so-called summer, when temperatures get as high as -30 centigrade. During the winter, temperatures plummet all the way to -80. It gets completely dark. Even the military aircraft that service the site cannot operate. So the station is so-called closed for about 8.5 months of the year. So if you see this, then you know that you're stuck for about another 7 months or so until the planes come back. So I've never done the winter shift. Every year we have to hire people that are prepared to do it. They're usually, hired guns. Sometimes somebody who's just finished their PhD will do it for the interest, but it's usually young people who are prepared to do anything once, right? I never did it when I was young. I might have done, but somehow that didn't happen. And I'm too old now. So just to, let's see. All right, so just dropping back to the very beginning, I know this is a semi-expert audience, but just for fun, right? Of course, we all know our star. Our sun is just a star, just like any other star, not a particularly big one, not a particularly special one. It is part of a galaxy, which is a decent galaxy. This is an external galaxy, but we think that our own looks rather similar to this one. So it's a spiral assemblage of 1 trillion stars. So, each individual star is absolutely insignificant. Many of them make a galaxy, but then even those galaxies are absolutely insignificant because there's a vast number of them. As we look out into space, we see just a huge number of galaxies fading off into the distance. The universe is absolutely vast, and we do not appear to be in the least bit special. So we obviously observe the universe almost exclusively. It's starting to not be completely true, but we observe the universe using light. And light is an electromagnetic wave. Obviously, it moves fast, but not at infinite speed. Any given packet of light, photon, ray of light, whatever you want to call it, can be characterized by its wavelength, the distance, the peak-to-peak distance, the distance between peaks of the electrical magnetic field. It's orthogonal propagation of electrical magnetic fields. Now, microwaves and radio waves are just longer wavelengths of regular light, right? So all light is, when we talk about light as astronomers, physicists, we include radio waves, X-rays, gamma rays. They're all just photons. They're all just light. So you're all familiar with the classical Doppler effect, and this happens, if we have 3 stars that are emitting rays of light, which would have the same natural wavelength, so they're from the same atomic transition, photons which would naturally have the same wavelength. If one of those stars is stationary with respect to us, let's imagine we're the observer over here on the right. If one of those stars is stationary, let's suppose the ray of light would be yellow. If the star is moving towards us, then the wave train gets compressed as it's being emitted. So it doesn't like animation, this is the problem. If the star is moving away, then the wave train gets stretched, and so the light is redshifted, it gets redder. Okay, so that's the kind of classical Doppler effect. It is caused by actual motion of things through space, right? Now, there was this guy, Edwin Hubble, about 100 years ago, and he was using a state-of-the-art optical telescope at that time to look at smudges of light that people have known about for centuries out there on the sky. And he was in the process of proving that those smudges of light, at least some of those nebula, are actually external galaxies to our own, and furthermore that they're receding. So what he did was he was able to measure the distance away that they were, and through the redshifting of the light, he was able to measure how fast they appeared to be receding from us. So we won't worry about how he got the distance, right? That's tricky, but possible. He was able to measure from the redshift the apparent recessional velocity. And so he found this very unexpected relationship, right? The further away a galaxy was, the faster it appeared to be moving away from us. It's a very strange result because it implies that we're completely special, right? The location of the Earth is the center of some explosion that went off sometime in the past. The things that flew off faster have gotten further away, and that's why the plot looks the way it does. So, this is an extremely weird idea because it makes us special again. And in fact, the simplest explanation of this is that the fabric of space itself is expanding. Now, it's kind of funny to say that that's a simple explanation because it seems very bizarre. But if you think about the analogy of coins on the surface of a balloon, as you inflate the balloon, as viewed from any given coin, all of the other coins are moving away. And the further away they are, the faster they appear to be moving away. The detail of this analogy is to make the galaxies coins. People often ask, are the galaxies expanding? Are we getting further away from the sun? The answer is no. In a galaxy, gravity is permanently one and bound the structure together. It's the intergalactic space which is expanding in this picture. So I like to call it the cosmological Doppler effect, right? And it hates animations. It will not show animations. So here we are at the center. Think of the yellow dots as being the fabric of space, right? The fabric of space itself is expanding. A galaxy so there's two galaxies, one that's twice as far away as the other, and they both emit a ray of light of the same initial blue wavelength. The further away one, the photon flies for longer, traveling through the space to get to us until it gets stretched more. The one that's closer has less distance to travel. The universe expands by a smaller factor while that photon is in flight. It gets stretched less. So the further away galaxy looks redder, but it's not because it's actually the galaxy itself is moving through space away from us. It's the space itself which is expanding, right? So this is a cosmological Doppler effect. It's completely distinct from the regular Doppler effect, right? There is no motion through space. People often worry in such a picture. They say, well, if you go far enough away, that galaxy is moving away from us faster than the speed of light, right? And that shouldn't be allowed. But it's not. No galaxies in this picture. I mean, the galaxies are actually all jiggling around a little bit. Call it peculiar motion. But in this picture, let's just imagine it's just a grid universe. And the galaxies are stationary with respect to that grid. Nothing is moving except the light through the space. Space itself is expanding. Another thing to appreciate is that, the more distant, the further away another galaxy is, the longer ago in time we see it, right? So this more distant galaxy, we see it as it was longer ago and redder. Okay, so Einstein, around the same time, actually, was cooking up his theory of general relativity, a generalized theory of space and time that blends them together into something called spacetime. I like to show this picture of him because this is what Einstein looked like when he was actually a dapper young man formulating the theory of general relativity. He's often pictured as he was later in life as a crazy-haired old man. But this is what he looked like when he was actually doing general relativity, right? When he was formulating the equations of general relativity. He actually fudged his equations. He put in an extra term, a lambda term, specifically to force the space-time to be stable, because he realized that in GR, space-time either tends to expand or contract, right? And he didn't like that. Everybody had known since the ancient Greeks that the universe was immutable and stable. So he deliberately fixed the theory to force it stable. And then later, when he heard about Hubble's observations of cosmic expansion, he called what he'd done here, his biggest blunder, right? So even geniuses have prejudices and make mistakes. So, okay, so the universe is expanding. It was known from the 1920s. By the 1940s, these guys were starting to realize, well, the logical conclusion of that is it must have been very hot and very dense in the past. Wind the clock backwards, the opposite of expansion, contraction. Everything must once have been all packed together in a small space. If you pack a lot of material into a small space, you make it hot, right? You compress gas with your bicycle pump. You can feel it getting hot, right? So they realized that once upon a time, the universe must have been hot and dense, potentially as hot and dense as the inside of our sun. The logical extension of that is, well, we should be able to see the glow. Hot objects glow. We should be able to see the thermal radiation from that early time. And so people were looking for it. In fact, these people were not looking for it. Some guys down the road at Princeton University were looking for it. They'd built a special telescope. But before they could actually detect it, these guys accidentally detected it using this large horn antenna that you can see in the background. So once that so-called cosmic microwave background, that redshifted thermal glow from the hot phase of the early universe, once that had been detected, everybody accepted essentially this hot Big Bang picture of the origin of the universe. So telescopes are time machines. As I said, we're looking back in time. In the present day universe, when we look out into the local universe, we see the rich structure of stars and solar systems and galaxies, the kind of grand design contemporary universe. As we look back, we can see back potentially to about 200 million years after the beginning, when the first stars were forming. That's what the James Webb Space Telescope is going to do for us. It's going to allow us to see back further in terms of seeing stars and galaxies than we've ever seen before. The microwave background comes to us from about 380,000 years after the beginning. That's when the universe, the expanding and cooling universe, made the transition from being plasma to being neutral gas. So plasma is opaque to light, right? In a plasma, you've stripped the electrons off the nuclei, and the light, which is the thermal light, which is present in the plasma, is ricocheting around, bouncing off the electrons and having its direction change. At about 380,000 years, the universe cools below about 3,000 Kelvin. It makes the transition from plasma to neutral gas. Neutral gas, like the gas in this room, is transparent to light. After that, the thermal glow is just free streaming through the universe. Each of those CMB photons is just on a straight trajectory, and the ones that set off from a spherical shell around where the Earth would later form, in the direction towards where the Earth would later form, those are the ones we're seeing today with our telescopes, right? Now, what we're trying to investigate with the latest generation of telescopes is what happened at the very, very beginning in this process called inflation. I'll tell you how we seek to do that. So again, when we make an all-sky map of the cosmic microwave background, here it's been projected, measured by a spacecraft and projected onto a sphere, onto a ball. Imagine we're at the center, we're in the middle of the sphere. What we're seeing when we look at the microwave background is a density, a sample of the density structure, which is the density structure which was on a shell cut through that infant universe. And so when we make such a map, we get an almost uniform glow from all directions with small perturbations from uniformity. So these areas that are shown in red is where the radiation is a little hotter, a little brighter, and in blue where it's a little colder, a little fainter. But those perturbations away from uniformity are like 1 part in 10,000, right? So the universe at 380,000 years, we can directly image it, and it was almost uniform. It was almost uniform plasma with small deviations from uniformity. And it's those deviations from uniformity that are the seeds from which all structure in the contemporary universe grew. So, when you see a blob here, that's where that gave rise to a supercluster of galaxies in the contemporary universe. We can't see that supercluster because the light from 380,000 years has only had time to reach us now, but presumably that galaxy supercluster is out there. All right, so how do we characterize the pattern, that blobby pattern that you just saw? So this is a kind of lump size histogram. On the x-axis is the blob size. It's a kind of inverted axis, so larger blobs are on the left and smaller blobs on the right. And then on the y-axis, it's just the amount of blobs. The colored points are data points from various telescopes that have measured the pattern. And then behind those data points, there's a dashed line, which you can hardly see because it hides behind the data points almost perfectly. That is a theoretical fit. So we can calculate, given just a few parameters of the universe, like the amount of ordinary matter, the amount of dark matter, the initial expansion rate, these sorts of things, just a few parameters, 6 to 7, we can make a theoretical calculation with extremely high confidence. So you do have to put in what are the conditions at the very, very beginning, simple statistical model of the initial conditions. You can propagate it through this plasma phase. It underwent oscillations, which is what causes these peaks in the so-called power spectrum. This is the power spectrum. And so by fitting the model to the data, you can find out what kind of universe we live in. And so the result is that it's about 2/3 to 3/4 dark energy being an energy density of empty space, about 1/4 dark matter, and about 4% of regular atoms, baryonic matter we call it, the stuff that we're made of, the Earth, everything that we can see, actually. So, okay, so that's one result that comes out of this fit. Another result is the expansion history of the universe. So we can infer how such a universe how it expanded in the past and how it will expand into the future. So this plot is showing on the x-axis time relative to the present. Here we are at time 0. And it's showing on the y-axis the scale factor of the universe. Think of that as the scale factor of the yellow dots on the grid of space in the animation earlier. So we'll define that scale factor to be 1 at the present time. And then the 4 colored lines show different possible universe models. So if it's an empty universe, it just expands continuously in a linear manner, and that would be the green line. Obviously, the universe is not empty. We see that it's got some stuff in it. If it had 100% atoms in this plot, 100% atoms in dark matter, then it would behave on the blue line. So initially it slows down, and it keeps on slowing down. If you make the amount of stuff 300% of what it is in this pie diagram, then you would live on the magenta curve. There would have been a big bang, the universe would coast, and then it would recollapse. It would coast to a stop and then recollapse into a big crunch. And that was a favored idea, 50 years ago. People thought big bang, well, nice closure, big collapse, big crunch. But that doesn't seem to be the case. In fact, the model that we live on is this red line, where initially there was a little bit of deceleration as the matter managed to slow down the expansion. At the present time, the expansion is just starting to accelerate. And in the future, it's going to accelerate dramatically and uncontrollably and end in blackness as everything is carried further and further apart on a tremendous tide of expansion. So that's what the data says, right? Uncomfortable though it may seem. Now, all of this does not explain the initial conditions. We can infer what the initial conditions were, that there was an equal amount of blobs of all sizes, and that those blobs had so-called Gaussian statistics, were drawn from the classical bell curve distribution. We put that in and it fits the data perfectly. It really does seem to have been the case that at some very early time, those were the initial conditions, but it does not explain why. There's no explanation as to why in this picture. So this brings us to this idea of inflation. So this is now a kind of super logarithmic plot of the evolution of the universe. It's starting to accelerate its expansion just now in the contemporary universe. We can look back to the microwave background, and then it's going back further in time to higher temperatures, to earlier times, nuclear fusion, the formation of protons. The idea is that at some incredibly early time, at some incredibly high energy state, there was a brief burst of exponential expansion, right? So the expansion in the contemporary universe is more or less linear. Yeah, it's starting to accelerate a little bit. But the idea is that at a very early time, there was a brief burst of kind of exponential hyper-expansion, right? And what that does is it takes initial quantum fluctuations and it blows them up enormously and makes them into real fluctuations, which are then the seeds of all the structure that comes after. So that's the basic idea. You know, these theorists cooked it up, 70s, 80s. Now, why do we want it, right? What does inflation do for us? So it solves something called the horizon problem. Should we try your computer? Oh, it's teasing us. This one's not animated. That doesn't explain it. I'm plugging that in. Okay, looks like you got somewhere. No, it's just back to me. But I tried to switch it to USB-C on here, so it should be listening to you now.
Is this the right?
Okay. Okay. See, that's pointing to the screen. We don't need that. Okay, is it working now? Yes. Okay. All right, sorry about that. So inflation solves several problems for us, one of which is called the horizon problem. So when we look, so we're here at Earth and we're observing light in two different opposite directions on the sky. We're observing light from points A and point B. This light has been in flight for 14 billion years, basically the age of the universe, about 380,000 years. So when we look in these two opposite directions, we see almost exactly the same brightness of microwave background glow. So that implies that these two locations at that time were at exactly the same temperature. How did they know to be at the same temperature? At that time, they were way out of causal contact with one another. Light itself had not had enough time to travel between those 2 points. It still hasn't, right? It's only reached us here in the middle. And in fact, it's just a curiosity. it will never reach, light from point A will never reach point B. The universe is expanding fast enough that it will be carried away on the tide and it can never get there. So this is a deep mystery, right? How can the microwave background be this uniform glow, given that the points that we're seeing it from have never been in causal contact with one another? So okay, so that is one thing that inflation can solve for us, because it says that these points, they actually were in causal contact, then inflation happened and blew them out of causal contact, and now the universe is reconnecting, causally reconnecting, right? So what inflation does is it takes a subatomic speck of a pre-existing space-time and blows it up so that it's far bigger, that speck is far bigger than the entire observable universe today that we can see, right? So it answers the question of why are those points at the same temperature by saying, well, once they were in thermal equilibrium, once they were in communication with one another. Inflation also solves the question, the so-called flatness problem. Now, in general relativity, space can either be positively or negatively curved, right? Parallel lines can either diverge or converge. The special case where they're actually parallel is an infinitely special case. Now, when we look at the real universe that we're in, we find that it's extremely close to so-called flat, right, where parallel lines truly are parallel. But there's no explanation as to why. So inflation solves the so-called flatness problem by saying, okay, in the before inflation, there was significant spatial curvature. Inflation took that curvature and it blew it up so enormously that when you examine the fabric of space-time on a local scale, where let's say local means the entire observable universe that we can see, it no longer looks curved. If you take the grid on the surface of the sphere and you inflate the sphere enough and then you examine it on the scale of just one cell of the grid, it no longer looks curved, right? Put it another way, if you're a stick man living on the surface of a big enough sphere, the curvature, the fact that the surface of the sphere is curved, is not accessible. You can't tell, right? Because on your size scale, it's not. So that's another thing that inflation does for us. So inflation is a tremendously popular theory, but it's also a completely wacky theory, right? Because it's saying that something happened in an incredibly high energy state. There was this burst of hyperexpansion. The whole of our universe came from quantum fluctuations in a tiny volume of space. So it's a pretty extreme theory. So it needs as much proof as we can get for it. So here again is this diagram where we've got this inflationary phase. Inflation will inject into the fabric of space-time perturbations of all kinds. It will inject density perturbations. They're shown here as waves, but you can think of them as just blobs. It will inject blobs of all sizes. And those blobs persist down to the present-day universe. As I said, they are the seeds of all the structure we see today. It will also inject into the fabric of space-time gravitational waves, perturbations, fluctuations of the space-time fabric itself, which is what a gravitational wave is. Now, those gravitational waves, they're spawned by inflation. They will travel down. They will be present in the contemporary universe, but they're incredibly hard to detect in the contemporary universe. So what we're doing is, so this is just to emphasize that the universe before the transition from plasma to neutral gas, when it was plasma, it was opaque. So we cannot use light to look back beyond the CMB. The CMB is the most ancient light that we can have. Any information, it cannot carry information to us from before the universe made the plasma neutral transition, because it was getting scattered around, right? Here it's showing the ray of light being scattered around off the electrons. It's only after the electrons get locked up in the nuclei to make neutral gas that light travels freely. However, the gravitational waves are coming down from inflation. They are present at the time that the universe makes that plasma neutral transition. and they induce into the polarization pattern of the microwave background a particular signature, a particular swirliness. Now, I haven't mentioned that the microwave background is polarized, right? You're all aware that light can be polarized, right? It can, each photon, you can think of it as having an orientation around perpendicular to the direction of motion. And so the microwave background has a polarization. We can measure it. We can make polarized maps of the microwave background. And then we can look in those polarized maps. Think of a polarized map as being lots of little pseudo vectors, lots of little headless vectors. We can look in those maps for the swirliness, the so-called B mode component in the jargon of the business. And we can look for B modes induced by gravitational waves at that plasma neutral transition, but gravitational waves that themselves come all the way from inflation, all the way from the very beginning. So that is what we're trying to do. So we are, in a sense, a remote sensing gravitational wave experiment. You've all heard about LIGO trying to detect gravitational waves here on Earth. They are looking for and finding gravitational waves from things like the merger of neutron stars. Comparatively recent events in the universe, right? We're trying to look for these gravitational waves, these very ancient gravitational waves from the beginning. You can't see those with LIGO. Their wavelength is way too long, right? But we can potentially see them through the signature which they write into the cosmic microwave background polarization pattern. So it's been a long search. This is another power spectrum plot. So it's amount of blobs on the y-axis, size of blobs on the x-axis. But now it's the amount of B mode blobs, right? The amount of swirliness in the polarization pattern. Now, the colored points are data, but they're little down arrows. Those are all upper limits. So these come from experiments. They measured the polarization pattern. They decomposed it. They looked for the swirliness, and they said, you know, swirls at this angular scale, which is angular scale of, say, 2 degrees. It's about 100 on the x-axis here. The amount of swirliness in the pattern at 2 degree scales is less than the point, the down arrow. Right? So less than some number that they can measure. Now, in the vanilla model, without any gravitational waves, we expect this solid red line due to an effect called gravitational lensing. I'm not going to get into what that is, but just try and take that on board. That solid red line is the expectation in the absence of gravitational waves. Then if you add on top of that expectation the dashed lines, the different values of this parameter R, where R is basically just the amount of gravitational waves. It's just a measure of the amount of gravitational waves. So that increment, that dashed line increment, is possibly added on top of the solid red, and therefore you can see it. If you can measure accurately enough, you can look for that increment. If you can't find it, then you're setting just an upper limit on how much gravitational waves there are, right? If R was 1, we would have seen them long ago, right? It would be easy, comparatively easy to detect. As R gets smaller, it gets comparatively harder to see that increment on top of the lensing expectation. So the name of the game is just to get the best possible experimental sensitivity and to look for these gravitational waves from inflation. Using my computer used to do it. So inflation is a controversial theory. One of the originators of inflation was Alan Guth, shown here. In 2013, the Planck space mission put out results, and he wrote a paper, kind of celebratory paper called Inflationary Paradigm after Planck 2013. There's a lot of things in the existing data that already suggest that inflation is true, is what happened. But then there's this guy, Paul Steinhardt, at Princeton, and he put out a paper in riposte to this paper saying inflationary schism after Planck 2013. Schism is a funny word for scientists to use, right? Schism is a matter of religion, right? A matter of dogma. But he actually put it in the title of his paper. So he is a determined denier of inflation. He thinks inflation is a junk theory. For reasons that often seem a little emotional, actually, and not very scientific. Anyway, it's controversial, right? Like very prominent theoretical physicists differ greatly in what they think of this idea. So here is our collaboration of experimentalists. We're experimentalists. I don't try not to have too many opinions about, theoretical matters. What we do is we build telescopes and we try and measure and we try and settle with data what is actually going on. So that's just a picture of our group, a mid-sized group, a lot of students and postdocs, a few professors seen here on the roof of the astronomy department at Harvard about a year ago. So the journey to the South Pole. So, I start from the Midwest. That's where I'm normally located, fly to the West Coast, and then fly down to the South Island of New Zealand, commercial aircraft. Then from the South Island, we fly by military aircraft into the coast of Antarctica to a base called McMurdo. And from there, we fly on up to the South Pole proper. So if you haven't paid attention to Antarctica, it's an enormous continent down there on the south of the world. It's covered by an enormously thick ice sheet. The ice sheet is about 10,000 feet thick. At the location of the South Pole, if it was to all melt, it would be about sea level. But there is an enormous mountain range that's submerged in the ice, the Transantarctic Mountains. McMurdo is down here on the coast, so that's where we fly in from New Zealand, and then we fly up to the South Pole. Just a few kind of slideshow of that process. So this is all done by under the auspices of the United States Antarctic Program, which is run by the National Science Foundation. So you go to Christchurch, New Zealand, and you go to the clothing distribution warehouse, and they kit you out as an Antarctic explorer. It takes, less than an hour. It's very efficient. They have lots of equipment. It's a big program. So then you go back to your hotel and you wait for them to tell you it's time to fly. Sometimes you go the next day. Sometimes you have to wait a week or even longer. This is me having just gotten out of this US Air Force C-17 military cargo aircraft at McMurdo. So I'm standing on the ice sheet there and wearing this ridiculous equipment that at McMurdo is complete overkill, but at the South Pole is actually very much needed. So McMurdo is a kind of what I imagine an Alaskan mining town is like. It's a dirty place. It's a supply base. There are huge fuel tanks. The reason it exists there is because it's the southernmost point to which you can get a ship. So once a year, a fuel tanker comes, and then a cargo ship comes to bring supplies. So it's quite a big operation, about 1,000 people during the summertime. We then fly on up to the pole. These are enormous, 14,000-foot peaks buried in the snow of the Transantarctic Mountains. And then we get to the pole. So this is unloading from one of the aircraft that service the site, a piece of one of our telescopes. This big blue thing is, a multi-thousand-pound hunk of steel. It's part of one of our telescopes, part of the superstructure being pulled out by this bulldozer. This is a picture of me at the actual geographic South Pole with 3 of my graduate students. It's an ice sheet. Right? It's a glacier. It flows by about 10 meters per year. So every year they have to relocate where the Earth's rotational axis is, and then they stick a stake in the ground at that location. So this is the actual South Pole. There's a ceremonial South Pole as well. This is the real one. So there we are. The thing to appreciate about the South Pole is that there is nothing there. It's an absolutely featureless ice plain. It's like a frozen ocean that extends for hundreds of miles in every direction from that location. The nearest piece of rock sticking out of the snow is like 300 miles away. It's completely flat. It's incredibly cold. It's an alien environment. There is nothing living there except the humans that have come on the airplanes. So why do we go there? Why do we do this at the South Pole? It's quite high. It's about 10,000 feet high. And that combined with the extreme cold means that the amount of water vapor between the surface and outer space is minimal. And water vapor is a killer at microwave wavelengths. It absorbs and therefore emits microwaves. So you want to go to the place on Earth where there's the least possible water. This is basically it. The fact that it's on the Earth's rotational axis is really convenient. You get one day-night cycle per year. And so the sun goes down, the atmosphere gets really stable, and we get really good quality data. There's good supporting infrastructure, there's power and cargo and data communication, there's food and accommodation, and there's even extremely limited entertainment. So it's a great place to do what we do. Our telescopes are actually refracting telescopes. They have about the previous generation had a 25 centimeter aperture, the current generation about a 50 centimeter aperture. There are two lenses that focus the light down onto the focal plane. The lenses are cooled to about 4 Kelvin. So this whole thing is inside a vacuum vessel. The light enters through a window, vacuum window, and then through two lenses down onto the focal plane. Very simple optical system, focusing those CMB photons onto detectors, which are cooled to about 1/4 of a Kelvin. So super cold cryogenic detectors in order to get the best possible sensitivity. Here is a picture of one of the focal planes. So the focal plane, this one is one of the previous generation. It's made out of 4-inch silicon wafers that have been lithographed and patterned using similar techniques that are used to make microprocessors and silicon chips. So if you zoom in on one of those wafers, this is a zoom in on one of the 4-inch wafers, you can see that it is itself an array of pixels. If you zoom in on one of those pixels, that pixel is made out of an array of slot antennas. So then this is zooming in still further on some of those slot antennas and the actual detector. The slot antennas absorb the microwaves. A summing tree adds up the electrical energy that's being absorbed in a phased array manner, and then the electrical energy comes down this strip line here and is dissipated into a resistor on a thermally isolated island. The temperature of that island then is then coupled to the intensity of the incoming radiation. And polarized incoming radiation, because the slot antennas only absorb photons of one linear orientation. So then you've got this temperature. We then have a transition edge sensor on that thermally isolated island, a sensor which is sitting right on the normal to superconducting transition. So it has an extremely high change in resistance for a very small change in temperature. And then we take that whole thing, we take the telescope and we scan it around, move it around, we move its pointing direction around on the sky. Think there's like a little reception spot which is coupling back to each one of these detectors, right? And so as you scan those reception spots around on the sky, this thing is tracking the intensity of the incoming polarized radiation. And then you read out the temperature using the transition edge sensor. You're making, you're sampling the differences in the CMB brightness at different points on the sky as you scan around. And from that information, we just read that out and record it to disk, and then we use it to build maps of the sky, polarized maps of the sky. So this is an animation that shows the telescope moving. I can get it to run. Maybe I can't. No, I don't think that's going to work. So this is the telescope during the daytime, right? These are black tubes of 4 baffles, which help to protect the telescopes from stray radiation at large angles. The telescopes themselves are inside this white box structure, and the light comes in through these black 4 baffles, in through the vacuum window, down through the lenses and to the focal plane. Okay, so in 2014, almost 10 years ago now, we thought we had found what we were looking for. We measured with the latest, greatest telescope at that time, these black points. And they looked exactly like the vanilla expectation plus an amount of gravitational waves equivalent to this R parameter of 0.2. And we were tremendously excited. We told everybody about it. There was a storm of media attention. We were on many front pages of newspapers around the world, which kind of surprised me because this is exotic stuff. And I didn't think that people cared about it very much. Obviously other scientists do, enthusiasts such as yourself perhaps, but I didn't think they'd put it on the Financial Times, right? They did, with a picture of a completely unrelated astronomy picture. And I was on Newsnight. I was interviewed by Jeremy Paxman. He just wanted to know how much it cost and who paid for it. But anyway, it was actually a lot of pressure, not a lot of fun. Actually, we were kind of amazed by the amount of attention. It turned out we were mistaken, right? The signal we were not mistaken about, right? That signal, it's there, right? But it turns out that it's not, even though it looks like a beautiful fit to the shape of this theory spectrum plus the vanilla expectation. It's not what we thought it was. It is the glow from polarized glow from dust grains in our own galaxy. So we're in a spiral galaxy, much like this one. We're about 2/3 of the way out. We obviously look up out of the plane when we make our maps. We pick an area of sky that's not in the galactic, not looking towards the galactic structure. But nevertheless, there is still residual dust up there, and it's radiating, and it's a little bit polarized. And so it basically corrupts our data, right? It adds in something that is not cosmological in origin. It's just coming from our own galaxy. This plot shows observing frequency on the x-axis and the amount of contamination on the y-axis. That map, those points that I just showed you were taken at 150 gigahertz frequency. That is, that's close to the kind of sweet spot. The contamination from dust gets bigger as you go up in frequency, and lower frequencies is another form of contamination that comes from relativistic electrons spiraling in the galactic magnetic field. That's called synchrotron radiation. So at low frequencies, that is the dominant contaminant. And so, you can see from this diagram why we picked 150 gigahertz. You can reduce the amount of contamination by going to the cleanest possible patch of sky, but you're still in trouble as you get down to R levels that are like 0.01. The contamination is greater than the signal that we're looking for. So how do you get around that? Well, we'd already started to make maps at multiple frequencies at that time. The atmospheric transmission is shown here by the black line as a function of frequency. And there's a window at about 90 gigahertz where the atmosphere is quite transparent. Another at 150, and above in the kind of 220 range, it's also pretty transparent. So we can make detectors that are tuned to those different frequency bands. And that's what we've done. So we've had a progression of experiments. We had BICEP 2, which produced the data that I just showed. Then we made 5 copies of that. We called that Keck array. So we built a bigger machine that could handle 5 of those receivers. And we diversified the frequencies. So we started off at 150, shown in green. For Keck array, we had 95s, and we also had 220 receivers. Then we built a bigger, more capable, more powerful receiver called BICEP 3. Which had many more detectors. The number of white dots is the number of detectors, essentially. This is showing the reception spots of the focal plane projected back on the sky. So that was BICEP 3. It was all at 95. And now we're building BICEP array, which has 30, 40, 95, 150, and 220, 270. It will have when it's complete. It's not complete yet, unfortunately. So that's like a larger machine, just a larger steel machine that carries the telescopes. So just to show you the maps, these are the 95 gigahertz maps from the BICEP 3 receiver. Temperature, total intensity is shown at the top, and then the Q and the U are the 2 components of the polarization pseudovector. So it's a pseudovector, so you can take the sine and the cosine. Those are the 2 components of the vector. We call them Q and U. On the right side is the noise, which is in the map. So you can see that we have extremely high signal-to-noise maps at 95 gigahertz. At 150 gigahertz, we've mapped the same area of sky. And as you flip between the 2, you can see that these patterns in the center of the field there, they remain exactly the same. That's because these maps are dominated by CMB polarization. As we move to 220, you can see again that the patterns are very similar, a little noisier. But look here on the right side of the map, these structures here, that's not CMB. That is polarized dust from the galaxy. It's not present at 95. As you go to 150, you can kind of see it because you know it's there from 220. The point is the dust has a different frequency spectrum information. So when you calibrate to CMB units, dust is getting brighter as you go up in frequency. And so you can use that to separate out. Oh, this animation is working. Look at that. So this is showing as a function of time as we add more years of data, right? So this is my life, 2012 through 2019. And we're adding in 2018, we're adding in more data. So initially we were mapping at 150. See, the red line shows where we're up to. And so as we add more data, the noise averages down and the signal comes into view. And then we added 95 to 20 and then the BICEP 395 receiver. So as time progresses, we average more data, we make a better map, we beat down the noise. So the latest results look like this, right? Once you have removed the dust and you're just plotting the CMB component, the black points agree with the solid red line adequately. There is no evidence, there's currently no evidence for gravitational waves. So that's unfortunate, that's sad for us, but that's the way it is, right? You do the experiment, you find out what the truth is. It doesn't mean they don't exist, it just means that we need to try harder, we need to build better experiments. Just gonna digress for 1 second to give a shout out to this guy. So he is shown in front of the Keck array, previous generation telescope. This guy's called Robert Schwartz, and he did 9 consecutive winter seasons at South Pole. Before that, he'd done 5 previous seasons. He did 14 seasons at South Pole, which is a world record. 14 winter seasons at South Pole, which is the world record. Now he is living in retirement in Germany, where he's from. So truly a heroic guy. So the latest generation experiment I mentioned is called BICEP Array. It's just 4 of these bigger receivers, just more. We built it in 2018-19 at the University of Minnesota. So we designed this crazy steel structure. We had the pieces made. They were made in Italy, actually, shipped to Minnesota. We reassembled them. And this is the fully assembled telescope with my team that built it. So we built the whole thing in Minnesota, and then we took it apart. Here's a extremely speeded up movie of the assembly. So the flashing of the light here is the day-night cycle, right? Those are days going by. And you can see the telescope superstructure taking shape. First of all, you have to build the superstructure, then you have to put all the motors and encoders on it to make it move, the drive controllers. Then we have to put in the support equipment for the cryogenic refrigerators. We have to put the actual receivers in. There's all sorts of moving parts, all sorts of electronics and computers that make it into a state-of-the-art CMB telescope. So you can see there the whole thing taking shape. And then, once we were done, we have to rip it all apart again, pack it into shipping containers, and send it off to the South Pole. We go down there, and as the parts arrive, we put it all back together again. So here it's reaching maximum completion, and now it's being taken apart again. And if we watch the video to the end, we would see the trucks come and get it, but I'm gonna move forwards. So yeah, here's the truck getting packed at the end. It's got all sorts of wonderful mechanical devices in it. That is a high pressure helium, ultra pure helium rotary feed through, where you can feed gas through it, but you can also rotate it. That's the inside of one of the receivers. The actual detectors are up here on the top, and these are my graduate students assembling it. That's Robert Schwartz on the way out of Pole after his 14th winter. I met him at McMurdo. This is taking out the old telescope. This is going to be trashed, a big crane removing it and lifting in a piece of the new one. And these are some of my students helping to put the whole thing together out in the snow. She's laughing because her fingers hurt so bad. These guys are trying to put in bolts. And when you start trying to put in bolts, you rapidly take your gloves off because you can't hold the bloody thing. And then your hands start to hurt really, really bad, really, really quick. And so that's what they're trying to do. See, they've got their gloves off. These are my students inside the telescope. So this thing is now big enough that you can have multiple people inside there. They're hoisting in one of the new receivers for installation. And this is the team in front, the tired team of people in front of the finished product. Although it's not finished, it's only got one of the new receivers on it. Since then, COVID happened, and that's knocked us back, and we haven't been able to proceed nearly as fast as we would like to have, but we're back, somewhat back in action, and last year we put in a second of the new receivers. All right, kind of at time, I'm going to summarize here. So the universe is expanding, right? It was once a hot, dense fireball. We claim, us cosmologists claim, that we understand its development all the way back to very close to the beginning. We know that it's 14 billion years old, 13.8, right? It's like it's supposedly a precision science. This theory of inflation says that the entire observable universe today came from a single subatomic speck and was hyper-expanded in a tiny fraction of a second, such that that volume of space-time now is bigger than the entire observable universe today. So that's a pretty radical theory. It demands as much proof as we can possibly get. If inflation really happened, it will have made a background of gravitational waves. Unfortunately, the theory doesn't tell you how much, right? It just tells you some. And you can tune the theories to make the amount very small if you wish. So we may be on a hide into nothing. We may never actually find these gravitational waves. But in the process of looking for them, we are constraining what models of inflation, what theories. We're ruling out whole classes of theories, basically. Theories which were previously very popular amongst the theorists, we're proving that they're not correct. So that's what we're doing. We're trying to detect the imprint of these gravitational waves in the polarization pattern of the microwave background, and we're trying to build the most sensitive telescopes that we can. We thought that we'd actually found it, but we were fooled by dust emission from our own galaxy, and as I've shown you, research is ongoing with bigger and better telescopes. Okay, thank you very much.
Time for a few questions for any. Firstly, how long do you think it would take to get back up and running the telescope, the new one that is in?
So the telescopes didn't stop running during COVID. We were able to swap out the winner overs and keep going. The problem is that in that first season, we'd only installed one of the new receivers, and there should be four to complete the experiment. So then in the 2021 and 21-22 seasons, we couldn't install a new one, but 22-23 last season, we were able to install a second receiver. So we've got two running now. They're not actually running quite as well as they should be, so we're still hoping to upgrade them and get them fully operational. We were not able to send a third one this year. It is in an advanced state of preparation and should go next season. The fourth one, presumably the season after that. So it's been a little painful that we've been strained. The Antarctic program was heavily constrained by COVID because it runs through New Zealand. New Zealand was totally closed, right? You may have heard in the press that New Zealand, they just closed the border and they managed to keep COVID out for a very long time. So that really impacted things. Then even last season, COVID finally made it to Antarctica, and then there were lots of panics because people were getting sick down there. And there's very limited medical capabilities in Antarctica, and the people that run the program are very risk averse. They don't want people to die down there. So, they medevac somebody, and then that was a big disruption to the program. So then they doubled down on testing and lockdowns. And so it's been things. COVID is mostly over in the rest of the world, but in Antarctica it's still a thing and still disrupting our efforts. But hopefully within a couple of years we'll be up to full power.
Questions?
Question.
Just going to ask, how long are you expecting the survey to run for?
Well, when you build a new receiver, kind of rule of thumb, you get most of what you're going to, it's a square root of time, right? You get most of what you're going to get in the first 3 years. You can go to 5, 6, 7, but then you got to go to 14, and that seems like too long. So, basically we want to complete the thing and then run it in the completed form at least 4 years. We're talking the end of the decade, really, before it's done, before this machine has fulfilled its purpose, and there's not much point in running it further. it's a slow business. It's become very hard what we're doing. Basically, is the problem. The need to dig through to get rid of the galactic foreground really slows things down, and there are other reasons why it's getting harder and harder. So yeah, it's a tough business. It's a tough job that we've chosen for ourselves. But everybody says it's important, and in fact, a super future experiment is being planned, which is supposed to cost a significant fraction of $1 billion. So that's how important people think it is. So I'm a part of that, but that's a bigger thing that will be a kind of next decade experiment.
The galactic foreground matched your predictions reasonably well. Do you think that's just a fluke, or is there?
So are you asking why the data points looked like the signal we were after? So that is, they were not really expected to, right? So the galactic foreground, and with further data, they don't really. So it just seems to have been a statistical fluctuation. So let's see, to go back much further. Yeah, this plot. So I think you're noticing that these points really do sit on that summation of the solid red and the dash curve. They sit right on the theory line. Now, the galactic dust actually has a spectrum that kind of comes down like this. It doesn't fall off to the lower L numbers. It gets bigger. So it's just a fluctuation of this particular patch of sky that we're looking at. Had we looked at another patch of sky, it wouldn't have looked like this, and we wouldn't have got fooled, actually. So we were unlucky. There you go, right? Noise fluctuates, and that's what error bars are for, right? The error bar tells you that it could be a different value, but yeah.